Je suis très heureuse d'être ici pour donner cet exposé. J'aimerais d'abord remercier professeur Stallet et l'Université Paris-Saclay pour cette opportunité exceptionnelle de faire de la recherche collaborative avec un des groupes, le meilleur groupe du monde dans cette région de recherche. J'aimerais remercier l'Institut d'optique et surtout Patrick Georges pour faciliter cette bourse, la bourse d'Alembert, et le groupe de Laboratoire Charles Fabry, Franck Delmotte, professeur Franck Delmotte, pour m'accueillir et pour notre travail collaboratif. J'aimerais continuer la présentation en anglais parce que les transparences sont en anglais. J'espère que vous êtes tous d'accord. So, as I was mentioning, I would like to thank the team at Laboratoire Charles Fabry and our collaborators at Lawrence Livermore National Laboratory and the Lawrence Berkeley National Laboratory. I would like to thank my laboratory also for supporting this sabbatical, for the Lambert Fellowship. Also our collaborators at the Synchrotron Soleil, the Institut de Nanosciences de Paris, and also outside France and the United States, collaborators at the Danish Technical University in Denmark and the group at the Instituto de Optica in Spain. And I hope I didn't forget anyone. So a little bit about the motivation for this work. As you heard from Frank, there are many fantastical science applications in the region of the spectrum that we call short wavelength region. And so for precision, I would like to define here is what you see as extreme ultraviolet, soft X-rays and hard X-rays. This is what we call short wavelengths for the remainder of this talk. And specifically, I'm going to emphasize here work that we did for the extreme ultraviolet and the soft X-rays. The hard X-rays will have to wait for another time, for another seminar. So there's all these amazing applications, and both our labs have been involved in those applications. As Frank mentioned, Livermore has done pioneering work on photolithography. The LSF group has done pioneering work on solar physics, and Livermore as well. And more recently, we have the emergence of these coherent, very bright sources, free-electron lasers, X-ray lasers, high harmonic generation, which offer, again, fantastic opportunities for research and which need these optics that I'm going to talk about. So these optics that we make, these coatings, are enabling components for these applications. So what is particular and difficult and special at short wavelengths, and why is it challenging to work in this regime? At short wavelengths, the refractive index of materials is complex, first of all, and less than 1. And with a real and imaginary part that these components here that are much less than 1. And so if you would like to use a lens like we use in our camera to take photos, you can't, because the transmission, if you look at the absorption length here, is almost 0. So lenses don't work. This is first message. Okay, lenses don't work, let's use reflective optics, let's use mirrors. Okay, let's take a mirror here. Frank has made this example of gold on fused silica. If you want to operate this mirror at normal incidence, the reflectivity is also near 0, so everything is 0. If you want to operate at really grazing incidence angles, very close to 0, then you will get some reflectivity, but if you want to go away from grazing incidence, it's going to be 0. So what to do? So this is where these multi-layer coatings come into the picture, as they say. They were first demonstrated in the 1970s. They consist of periodic stacks of alternating materials that you see here. And you can have 2 or 3 materials, and you can have periodic or aperiodic stacks. For this talk, we're going to limit ourselves in periodic structures. And so where before you were going to have 0 reflectivity out of a single layer, now with the constructive interference of the electric field amongst these layers, which are about 50 in this case, 50 periods, about 100 layers, you can have a reflectivity that is very close to 1. And So you can think about the structure in terms of it being a synthetic crystal because it functions according to the Bragg law that we have for crystals. Only in this case, instead of the interatomic distance between the atoms, in the crystal you have the thickness of this bilayer, which we also call period or d-spacing of the multilayer. And so the peak wavelength is governed by this equation, which is the Bragg equation. M is the Bragg order. We talk about M equals 1 for most of this presentation. Lambda is the peak wavelength. D, as I mentioned, is the period of this coating. Theta is the angle of incidence from grazing. And this is a factor that represents the refractive index. Delta is part of the refractive index, which is a small correction, basically. So you can see that the normal angle of incidence, where theta is 90 degrees, this thickness needs to be approximately half of the wavelength of operation. You would think that all of this sounds very straightforward, right? Pick two materials from the periodic table, make a multilayer for the right wavelength and angle of operation. It is not straightforward because it is difficult, very difficult essentially to make these coatings. They have to satisfy very particular requirements. First of all, for the design, you need to have a very good knowledge of the refractive index, which you don't, as I'm going to discuss in a moment. You need to have the ability to deposit continuous nanometer scale layers. You need to have layer-to-layer thickness control across large curved surfaces in order to make large mirrors, for example, for NASA and photolithography. You need to have sharp and smooth interfaces. And very importantly, these structures need to have long-term stability over months and years. So these requirements are very difficult to meet. And I'm going to address them in this presentation, except for this requirement here. Again, I'm going to leave it for a future presentation. I'm going to talk about these four, basically. So to the fundamentals, how do we design multilayer coatings? This is an example of a multilayer stack. Once again, you can have more than two materials. Here, to keep things simple, I'm showing just two materials. So you have a specific photon energy of operation. For example, you want your reflectivity to peak at about 28 nanometers, as we're showing here, or 46 nanometers for a different multilayer. These are two different coatings. So pick two materials based on the available refractive index values that you have, that have good contrast in this photon energy region, in this wavelength region. And then adjust the ratio between the two materials to get the right peak reflectivity and the right bandwidth. I should mention here, it's very important, lots of multilayer coatings operate in the region below the absorption edge of their constituent materials, because there, this material that is part of the multilayer has low absorption. So it can have very good contrast with the other material and produce high reflectivity. So multilayers typically operate near absorption edges. So you feed these parameters in the Fresnel equations, and you develop a model, a design model for your coating. You deposit your coating, you measure it. I'm going to explain how you measure it in a moment. And then you adjust your model parameters so that you can have a beautiful fit of the data like we're showing here. So this sounds pretty straightforward, except we don't know a important set of parameters here. The refractive index, the interfacial roughness, and the interdiffusion between the layers are not well known for short wavelength materials. And these are very important parameters for the model. Furthermore, they cannot be determined theoretically, as I'm going to explain. You need to determine them experimentally. And so this is why this is challenging to do, why it is challenging to make these coatings, because these very important parameters here are not well known. So with this introduction in my presentation, I'm going to make a short if you like, introduction in the experimental facilities for deposition and characterization of these coatings. And then I'm going to address the main topics of my talk, which are the essential refractive index measurements of multilayer materials, investigation of the effects at the layer interfaces, and finally, the lifetime stability of these coatings, which is very important. So first, on the deposition facilities, we use a technique called magnetron sputtering, or in French, pulvérisation cathodique, which briefly, you have your material target that you want to deposit. You apply a magnetic field below your target. Under vacuum, you introduce a process gas. You create a plasma. And through this plasma, you get your deposition onto the substrate, whether it be a flat or curved optic or a grating or anything else that you may need to deposit on. This technique has been maturing for the last 30 years. And without getting into details, it has all the right properties to make this type of coating for this wavelength region. I should emphasize here something very important that often comes up as a question. The conditions during magnetron sputtering are not at thermal equilibrium. Therefore, we cannot predict exactly, theoretically, using thermodynamic codes and other theoretical calculations, we cannot predict exactly how two sputtered nanoscale materials are going to react with each other. We cannot predict what is going to happen at the interfaces. We cannot predict if they're going to form islands or continuous layers and whatnot. Therefore, experimental investigations are needed for all of these effects. Just to give you an idea, these are our deposition systems at Lawrence Livermore on the left and at LSF on the right. These are, again, vacuum systems, magnetron sputtering systems. They operate in a planar geometry. You basically have your substrate on a platter, which is rotating at about 1 RPM velocity underneath or on top of your sputtering target. So you pass under one material, then you pass under the next material, and this is how you make the multi-layer. And of course, you need to have a very good method, very precise method to control the thickness, which I'm not going to discuss in detail in this presentation. We'll have to leave something for the next presentation. So again, a few words about our characterization techniques. At 8 kV, using a copper K-alpha source is a basic in-house laboratory measurement, very important measurement. We all have this system in our labs right next to our deposition systems. With this measurement, you can see the first order of the multilayer as well as higher orders. Again, in most cases, this is not the photon energy of operation of your multilayer, but you can still use it to characterize your multilayer. And from this measurement, you can determine the structure of the multilayer, the layer thicknesses, roughness at the interfaces, density of the material. So this is one basic characterization. We also have here a suite of other characterizations. AFM and TM and SEM can provide highly localized information about morphology and crystallinity. XPS, RBS, and NRA can give information about density, atomic and chemical composition. And finally, one of the most important characterizations is at wavelength reflectometry. The ultimate test is to measure your coating in the photon energy where it is going to operate. So for this presentation, we have used beamline 632 at the Advanced Light Source Synchrotron, Lawrence Berkeley Lab, metrology and test beamline at Soleil Synchrotron, and our collaborators in Spain, the Gold facility. So the first topic is the fundamental need for refractive index measurements of multilayer materials. Turns out the refractive index of materials at short wavelengths is not well known. I'm showing here this reference, which is known in the community as the Henke tables. It is a definitive compilation of refractive index values, which is also maintained on the web by the Center for X-ray Optics at Lawrence Berkeley Lab. These are our collaborators. I'm sure that lots of you have used this database at some point to obtain refractive index values for your calculations. It is a compilation of experimental data from the 1900s to about 1980, combined with theoretical calculations, which assume that matter behaves in an atomic-like manner. This assumption, as you know, is not true near absorption edges. And therefore, in the vicinity of those absorption edges where you have interatomic effects and intraband transitions and other chemical effects related to the chemical environment, you need to do experimental measurements in order to determine the refractive index of materials accurately. And it turns out that since 1993, only 15 elements have been updated with experimental data, which is not a lot. And furthermore, for compound materials, these, again, atomic-like approximations are not accurate, and therefore you need dedicated measurements for compounds like carbides and oxides that we found in these multilayers. So statistically speaking, if you look at this table, chances are the refractive index values you are using are not very accurate. And here is an example. We made the chromium boron carbide multilayer, and we measured it, and we tried to model its performance in the vicinity of the chromium L23 edge. And it turns out that the available values for chromium fail very badly to predict the shape of the multilayer, and also this peak here, who turns out belongs to the chromium L2 edge. And so it's very surprising because chromium is a very important material for science and technology. At the same time, it's not surprising because these measurements are extremely difficult to make. Just a few of the challenges here I'm highlighting. You need a perfectly bright, perfectly monochromatic, well-characterized light source, calibration facility. You need extremely thin freestanding thin films, about 10 to 100 nanometers thick. And if you do reflectivity measurements for your refractive index, you're also very sensitive to surface roughness and contamination at the monolayer level. So we decided to do these very important measurements for the refractive index of chromium, since it is a very important material for multilayers. This work was led by Frank Dermott. So I'm showing here first the thin freestanding chromium films that were up to 20 nanometers in thickness and thicker. They were prepared and mounted by our colleagues at Lawrence Berkeley Laboratory, and you can imagine that these films have to survive the pump down in vacuum and venting that are thinner than, they're just a few atomic monolayers thick, basically. And so first we had to do that. And then we had to do measurements in an extended photon energy range that starts at about 20 eV and goes to about 1 keV. This means we had to change lots of settings at the beamline for those of you who are familiar with the synchrotrons. And I hope you can appreciate the nice continuity of the data that we got, the overlap. I'm showing here 3 out of the 6 films that were measured. And then you have to deal with imperfections of the light source. In this case, we determined that the light source has 1%, just 1% of spectral contamination that happens to be in this region of the chromium L23 edge, where the absorption due to the monochromatic beam is higher than the absorption due to the spectral contamination. And there is no straightforward way to remove that contamination. So Frank came up with a very clever model, and he was able to remove that contamination effect, which presented the problem in the analysis of the data. And so finally, we were able to analyze this data. And from those data, you obtain directly the absorptive part of the refractive index, beta, and then you combine them with other absorption data outside the range of the measurements, and you do an integral transformation, Kramer's chronic transformation, to obtain the real part of the refractive index, which is delta. And so it's pretty complicated, and it takes a lot of work. But we succeeded. And in this fashion, we were the first to demonstrate the splitting in the L23 edge of chromium and also in the M23 edge of chromium. And you can appreciate that there's a difference of up to a factor of 3 between the old tabulated values and the new values. And we were very happy to see that now our new refractive index values for chromium can fit the measured reflectivity data very well, including that small peak here. And so our measurements are validated by this fit. So our efforts were worth it. So I'm going to come back to this subject at the end of the presentation. I just wanted to say that it is a very important subject, not only for the multi-layer coatings that we're talking about today, but also for atomic physics and material science in general. And there is a great need for these measurements. Okay. So we also, just to show you that this is ongoing work, we very recently studied the refractive index of platinum in the vicinity of the N and O shell absorption edges. We used again transmission measurements and also reflectivity measurements, reflectivity versus incidence angle for a few photon energies in the low part of the spectrum here. And when you do reflectance measurements, you can fit both delta and beta directly from the reflectance data. And I'm showing here our data again. There is fine structure that was missing. The red curve here is the tabulated values, and you can see the difference and the detail in fine structure that our measurements revealed. This is our measurements by transmittance, the dark blue, and reflectance by light blue. This is the real part, and this is the imaginary part. Again, you have a beautiful resolution of the O and N edges, which did not exist before. And so again, this is ongoing work that we're doing. So with that, I'm going to go to my next topic, which I mentioned in the beginning of the presentation is very important, is the investigation of interfacial effects at the interfaces between each of the layers in the multilayer. Again, this is something that cannot be predicted theoretically. It has to be investigated experimentally. And what do I mean by interfacial effects? This is a simplification, which I hope helps you understand better. We can roughly separate these interfacial effects into two categories, roughness and diffusion. In reality, both phenomena happen at the same time. By roughness at an interface, we mean the height variation at the interface, which leads to loss of reflectivity due to scattering. You don't want to have that. In extreme cases, you may even have discontinuous layers in the multilayer. And the other effect is diffuse interface, meaning diffusion of one material into the other. There you lose reflectivity due to diminished optical contrast between the two layers. You may have compound formation at the interfaces. You may have density and compositional changes, microstructure changes, and you may even have an entire layer be lost inside the interface. And we're going to see that in a minute. So we decided to investigate this phenomena using this chromium boron carbide multilayer coating. This is a coating that has been pioneered by the group at LSF due to its potential for high reflectivity in the regions of the boron K and chromium L and K edges. As I was mentioning again, below these edges is where boron or chromium have low absorption, and this is the chance to get high reflectivity. So we very often operate at these photon energy regions. So I'm showing here peak reflectance versus photon energy at specific angles of incidence, and NP is the number of periods in the multilayer. So again, you can see the high potential of this coating and the high reflectivity that you can achieve. This is work that was done by working with Catherine Bourclain, a doctoral student in the LSF group, advised by Frank, who is now working as a postdoc in my group at the Lawrence Livermore Lab. So we can extend our collaboration with Catherine. So we decided to investigate, again experimentally, the interfacial effects in this coating. So we're taking a closer look in the multilayer structure by doing cross-sectional transmission electron microscopy, or TEM, that I was mentioning earlier. Here we have two different samples, sample 1 and sample 2. Both of these samples have the same targeted thickness of chromium layer. It is 2.5 nanometers. The top sample has a targeted boron carbide thickness of 5.7 nanometers, while the bottom sample has a much thinner boron carbide layer of 1 nanometer. First observation clearly is that the top sample has a well-defined periodic structure, while the bottom sample seems disordered, non-uniform, with loss of contrast between the layers. If we do a detailed analysis of the gray value in these images, we can see that on the top sample, the good sample, there is an area here where it has a shoulder which represents an area where the boron carbide and the chromium layers have interdiffused into each other, and is shown here in this schematic as its interface layer. We determine that this layer is about 1.5 nanometers thick. As for the bottom sample, which has 1 nanometer thickness B4C layer, we determine that the entire B4C layer has been lost at the interface. So you don't have chromium and B4C anymore, you have chromium and an interdiffusion layer. Because of this phenomenon, because of the general disorder and loss of contrast that you see in this sample has nearly zero reflectivity. So we pursued further measurements of this top sample, which is shown here in this curve, at different photon energies. And we determined that this interfacial layer that I was showing in the previous slide, it is essential that it be included in the model that we make for the multilayer. Otherwise, you cannot get an accurate representation of the reflectivity. And I'm showing here again the measurements of this sample. If you use the 3-layer model and you include the interdiffusion layer, you can have a beautiful model. And actually on all 3 samples, there is two other samples that I'm showing here that we measured at Soleil. If you only try to make a model with just the chromium and B4C layers, you will never be able to predict the reflectivity accurately. So the takeaway from all of this study is that you need to investigate interfacial effects separately using independent techniques and then incorporate them in your model, if you want to have a realistic design for your multilayer coatings. Additionally, I wanted to mention about this material system. We mentioned this reflectivity after 3 years after deposition. And the reflectivity was unchanged. So this is a very stable reflective system that can be used in applications that require a long lifetime, and we're very happy with its performance. It also means that this interface layer is very stable over time, and it does not hinder the stability of this coating. My final topic is what I was just mentioning for the chromium B4C multilayer, is the concern about lifetime stability of these multilayers. And by lifetime stability, I mean the performance of the coating as measured right after deposition, or a few days and a few months after deposition, and longer time scales. So why do we care about that? Is because I need to start this movie, if you excuse me. There it is. Is because of applications such as the space-borne telescopes that Frank was mentioning for EUV solar physics that require stability over 15 years for the optics. These missions aim, such as the Solar Dynamics Observatory that I'm showing here and the GOES space weather satellites, want to look at the sun's atmosphere at these short wavelengths. Why is my movies keep moving? They want to investigate questions such as the heating of the solar corona, and they want to investigate the extremely complex magnetic field and plasma of the solar corona, with ultimate goal to answer questions, such as the reasons behind the coronal heating and the prediction of events such as the solar flares and coronal mass ejections that can affect our life here on Earth. So what happens is, between the time that these mirrors, these coatings are deposited and the launch of the mission, several years, for example, 5 years can elapse, and then the mission is required to have 10 or 15 or 20 years lifetime. So this is how you arrive at this requirement. And my lab was involved, again, in the development of these coatings. I'm showing here 2 different coatings per telescope for the Solar Dynamics Observatory. The numbers that you see here is the peak wavelength in angstroms. And here for gauze, we did 6 different wavelengths, 6 different coatings, 60-degree segments for six different wavelengths. These are the same wavelengths that are important for coherent light sources as well. And what happened here is because we had this lifetime stability requirement, we had to sacrifice reflectivity for stability. This means we had to use coatings that have less reflectivity because these coatings had better stability. In the future, we want to be able to use coatings that have both high reflectivity and high stability. And I'm going to talk about developments that we made in this direction. So here is an example of improvements in stability. We are very interested in this wavelength region from 25 to 80 nanometers. It is a region, again, where there is lots of solar plasma emission lines, iron lines, helium lines, other material lines. And these are the same emission lines, of course, that are important for coherent light sources. So we want to do imaging in this wavelength region. And there is a material system, magnesium silicon carbide, that works very well in this region, as you can see here. It is because this region is right below the magnesium L edge, and as I was mentioning, you have a low absorption, and therefore you can achieve high reflectivity in this wavelength range using this material system. In addition to high reflectivity, you have a set of other good properties for this coating. It has near zero thin film stress. This means that the coating is not going to delaminate from the substrate. It has very good thermal stability to high temperatures if you need that. It has a good spectral selectivity. As you can see here, it is nice and narrowband so that you can select a single spectral line. And so at first glance, it looks like it could be the best multi-layer coating for this wavelength region, except you have a very, very serious problem with this coating. You have atmospheric corrosion, which is caused by the presence of magnesium, which is a corrosive material. And that leads to catastrophic effects that you see here. And so this material system is being prevented from use in applications that require long-time stability. I want to mention that this material system was a candidate for the Solar Dynamics Observatory, for example, but again, we couldn't use it because of corrosion. We had to use materials with lower reflective performance and better stability. So what you can see here is this catastrophic corrosion. This is a scanning electron microscopy, SEM image of the top surface. It appears spontaneously and suddenly after a few months in air. You see here regions that seem to be exploded on the top surface of the multilayer. This is a zoom. These regions you can see here, they look like a crater that has just exploded. Material seems to be missing, or material is peeling off, like you peel off a sticker almost from the surface. And there is other regions of the coating that seem to be about to erupt. They are expanding and are about to erupt. So what is this? What is going on? We decided to investigate this effect in detail. Again, we started from one of those SEM images, and we did cut a cross-section. Let me go into the zoom mode again. So we went into out of those craters, we cut a cross-section, and we did cross-sectional TEM. Here is the multi-layer. You can see it. And then on top of it, you can see the corrosion products. And you can see, interesting, we notice that there is 4 layers, bilayers, that have been completely consumed by corrosion and are missing from the top. You can see here the corrosion products forming, which we did X-ray photoelectron spectroscopy, and we determined that they are brucide and hydromagnesite. They're basically corrosion products of magnesium. And because these corrosion products come with volume expansion, this is why you have these eruptive effects, and you have basically the multi-layer coating almost exploding with this effect and basically being destroyed. So the question is, how did this phenomenon start, and how did you get to this point? One day you can have the coating looking fine, and then a couple of months later you can go and it's completely destroyed. So we continued our investigation, and we selected a sample that visually seemed okay, but upon closer inspection with SEM, you can see the origin of corrosions already beginning. And we determined via this characterization that I will explain in a moment that atmospheric corrosion attacks the coring from the top surface. The top surface has a silicon carbide capping layer, but it is not enough to protect because it has to be thin to preserve the high reflectivity, about 100 nanometers, let's say. And at the same time, this top layer has defects and pinholes which are inherent in these corings. So aggressive ions in the atmosphere, like chlorine and hydroxyl, attack the coring from the top surface, and they start forming corrosion products. You can see here the corrosion product in the magnesium layer. And once they attack the first magnesium layer, then this effect propagates in the layers that are underneath, and you basically end up having these catastrophic effects. So we decided to try and find something that can protect from this catastrophic effect. So basically, you need a barrier that protects from corrosion while maintaining high reflectivity and all the other good properties of this multilayer. So putting a film that is extra thick on top of the multilayer is not going to help you because you're going to lose all of your reflectivity. So you solve the corrosion, but you don't have a good multilayer anymore. So we thought that aluminum is a material that is transparent in this wavelength region, so it doesn't reduce the reflectivity, and we discovered that when it is deposited on top of the magnesium layer, the two layers diffuse into one another spontaneously. We were the first to observe this phenomenon, and from crystalline, they become nearly amorphous. And so you have this nearly amorphous aluminum-magnesium layer, which is pretty thick. Here, in this case, it is about 40 nanometers. And it forms a barrier that can be pretty effective against corrosion. And you can have this layer. You can put this corrosion barrier in one of the magnesium layers, or you can put it in 2 or 3, or you can put it in all the layers in the multi-layer. And it can be, again, underneath the topmost silicon carbide layer, or it can be at the bottom of the multi-layer structure, or you can put it in all the magnesium layers with very small penalty in reflectivity. And as you can see here, we have aged this sample for 2.5 years, and there is almost no corrosion. So again, this development was demonstrated a few years ago, and we have since implemented this coating in the lab, and there is groups around the world that are trying it, and we are hoping that this material system is going to be used in future space missions. I'm going to show you here the amorphization of this coating. Here you can see the magnesium and aluminum diffraction peaks of the coating just a few days after deposition, and in the red curve that you probably can see is a little bit faint, you can see that a few weeks after deposition, these peaks are almost gone, again demonstrating the amorphization of this coating. So as I mentioned, we implemented this coating in actual, multi-layer coating designs. This is just an embodiment, just to have fun. We planned the first Bragg peak of the multi-layer to be at an oxygen neon plasma line, and the second Bragg peak at another neon line at 46 nanometers, the third Bragg peak at an iron plasma line. Of course, again, this is an example. You can tailor the coating to have specific peaks at selected emission lines of interest, or to be broadband and cover a broadband range. You can customize the design of this coating for coherent sources or solar physics or other applications. And you can do imaging or spectroscopy using this coating. So this brings me to the conclusions of the talk. I hope I gave you an idea to the challenges and triumphs that we have been having in this research, very rewarding research. Again, short wavelength multilayer optics are really enabling components for many science experiments and applications. During this fellowship, Jean d'Alembert Fellowship, we have determined improved values of the refractive index of materials. We have developed new multilayer material systems. We have understood experimentally interfacial effects that are very important for the design of multilayer systems. We have developed corrosion barriers and implemented corrosion barriers to achieve longer lifetime for those multilayer coatings. And using all of those tools, we are going to feed them back in our models to develop new multilayer designs with improved experimental performance. We have a graduate student in the LSF group, Jennifer Rebelato, who's here in the audience, who is working on this the design of advanced multilayer coatings, and we're very happy working with her. And finally, I wanted to emphasize one more time the importance of pursuing investigations of the refractive index for the additional materials, including compound materials, carbides and oxides. We believe this topic is important not only for multilayer coatings, but for atomic physics and material science in general, and is something that we plan to pursue in the future. I thank you again very much for your attention.
Pour cette très intéressant talk. Et c'est vrai que quand on utilise ces outils, on n'imagine pas souvent la physique qui est derrière. Et malheureusement, vous n'avez pas eu le temps, mais aussi la technologie peut-être pour faire ces films alternés et très fins. Donc nous avons le temps des questions. Je suis sûr que tout le monde veut savoir beaucoup de choses. Qu'est-ce? Attendez, on va attendre le micro.
Yeah, thank you very much for inspiring talk. So in the previous part where you discussed the chromium B4C and
yes.
the interface region,
yes.
Is that stable because of compound formation in that region?
That is a
Did you study the...
Well, very interesting question, a very good question. We did try, we tried to do XPS measurements, and we have XPS results from this coating to determine the chemical state of the materials inside the multilayer. The problem with XPS is you have a limited penetration depth, about 100 angstroms, so you can only look at the top layers of the coating. If you do depth spatter and you want to go deeper, you risk altering the material, the layers, because chromium is reactive B4C can react to C, so by depth spattering you can change the conditions. So it's a very challenging study to do, but we did study the top layers. We don't have conclusive evidence that there are compounds. We saw that there may be some oxygen compounds and nitrogen compounds with boron in the top layers, but again, this is the very top of the multi-layer. So there is definitely intermixing. We're not certain that there are compounds, and it's very likely that there may not be any compounds, but it's something that is very, very hard to determine. And especially after we saw the very good stability of this coating, after 3 years, we were reassured. But it's something that we may continue to pursue in the future if we want to get to the bottom of this question. But we haven't gotten 100%, but we tried.
C'est très intéressant. Juste par curiosité, est-ce que la prolifération de sources, surtout, je pense surtout à la génération d'harmoniques, mais d'autres sources laser dans ce régime, est-ce que ça promet de vraiment améliorer les mesures d'indice de réfraction? Parce que vous avez beaucoup insisté sur le fait qu'il manque des données.
Yes.
Donc, est-ce qu'on voit que les sources qui arrivent vont améliorer, vont augmenter la quantité de données disponibles pour vous?
Yes, this has already started, the availability of synchrotron sources that are needed for these measurements. This has already started from the mid-90s, one can say, when fourth generation synchrotron sources came into the picture. And again, it is a testament to the quality of these sources, such as beamline 632 at the advanced light source and the Soleil beamline, that we are able to do these measurements. So the answer is yes. It is because of the existence of synchrotrons that we're able to do measurements that are so accurate. And that is why, as I was mentioning earlier in the talk, there are measurements dating from the 1900s to the 1980s already incorporated in the data tables. They're not as accurate as the measurements that we did after. And this is because of synchrotrons. But you can see that it is, the methodology is very, very complicated. And as I was explaining for chromium, even 1% of spectral contamination in a photon energy region that is important for the measurements can completely throw off your measurement. So even with those advanced facilities, there is still a very heavy burden on the measurement and the post-measurement analysis. So they're not easy measurements to make. However, again, I will say that synchrotron sources enable this measurement. It is synchrotrons that are needed to do this type of measurement.
So you showed a very, very nice result on the measurement of the chromium index. Do you plan on measuring some index for more materials? And if so, do you plan on publishing it somewhere? Is there somewhere where we can get the tables for our code?
Yes. Thanks, David. As I mentioned in the talk, yes, we are. This is a topic that we feel is, again, very important, not just for multi-layer coatings, but for the entire community. And so this is something that we're planning to pursue in the future. As I mentioned already, we were looking at platinum, and we also have some tungsten data that we're analyzing at this moment. Eventually, we plan to incorporate the new refractive index values in the tables. For the moment, you can obtain them from us. And there is also a publication that gives you all the information that you need to know, about how these measurements were done and how this compilation of values was constructed. So talk to us.
Thank you for the talk. And I have two questions. One is about the aluminum magnesium coating. When you add this extra layer, do you add also some stress to the multi-layer coating?
No, we have measured the stress of early samples that we made. The stress is virtually unchanged. The stress of magnesium silicon carbide is very close to zero. And so you remain just a couple of 100 megapascals, which is considered low stress. So that's a good thing about these barriers.
Great. And another question, is there any way to study the lifetime effect or aging effect more quickly, not to wait for many years?
Yes, that is a very good question that comes up very often. There is no easy answer, and no one solution fits all systems. There is things you can do. For example, for this corrosion problem, you can imagine putting the coating in a more humid environment where the chance for atmospheric corrosion is higher. You can imagine other accelerated tests. One test, which I will mention with a lot of caution, is you can gently heat the multi-layer, anneal it basically, and that can give you some information about the stability at the interfaces, because when we start annealing these coatings, you start seeing effects at the interfaces at some point which start degrading the performance. Either you have compound formation or one layer starts interdiffusing into the other. So annealing can give you some information about the stability of the interfaces that may or may not be related to long-term stability. But you have other effects such as oxidation that happens from the top surface. And I wouldn't know how to, maybe you can put the sample in an environment when there is a lot of atomic oxygen. So depending on what is your problem that you're worried about, you can put the sample in an environment where that problem is enhanced and accelerated and try to test it like that. But it has to be examined on a case-by-case basis.
Okay, thank you very much.
Bon, mais il semble que les gens veulent réserver pour votre prochaine présentation et votre prochaine venue à l'université, veulent réserver leur temps. Donc je vous remercie encore une fois d'être venu parmi nous et de nous avoir donné cet très intéressant talk. Et j'espère que vos travaux vont continuer avec beaucoup de succès et que j'aurai peut-être un jour l'occasion d'utiliser dans des facilités telles que XFL ou je ne sais je ne sais quoi. Je vous remercie.
Merci.